Great, nice. Now, I call these fun challenges. Now, to some of you, they might not be fun, and to some of you, they might not be even all that challenging, and that's fine. What I mean by challenges is that these are just questions that are asked in a slightly different way, where you have to kind of decide, how can I solve this problem? Where it's not just like a routine procedure, like every single time I see this, I do that, like the majority of your questions will be, and that you practice the same thing over and over again. These might just be asked in a different way, and maybe we use a different concept as well, like we're using area and perimeter, and we combine that with the idea of exponents. Okay, let's jump in. If we look at the first one, it says that if x is equal to -1, so they're actually giving us a value. They're saying that x is -1 and y is equal to 1. So we can do some substitution over there. But why are they giving us? Then what is this equal to? So they're giving us that x is -1, y is equal to 1, and they want us to figure out. So then if I've got x, which we have, y to the power of that, they're obviously huge exponents, to the power of 101, to the power of 200, and they want us to figure out what that is. Now, you can pause and try this on your own. I think a lot of students would maybe reach for their calculators, which I guess is fine. The whole idea is that to do this without that. So it's actually not okay to just reach for your calculator, because there is a concept that we are trying to develop. Sometimes you won't be able to do this with your calculator. You need to use your brain if we change those values from 1 to 2 or whatever the case may be. So we want to develop the understanding and the concept and not just always reaching for our calculators. Well, let's go substitute. We've got that x is a -1. I'm going to put it in brackets because it's a -1 and they need to kind of stick together. To the power of 101 plus y, which is just 1. So that doesn't really need to be in a bracket, but I mean, we can do that, to the power of 200. And we need to get that value. Well, the basic idea or basic principle over here that we just need to remember is that what is 1 to the power of 1? Well, that's just 1. 1 to the power of 2, it's still just 1 times itself, which will give us 1. If it's 1 to the power of 10, it's still just 1 times itself 10 times. So if we're going to make one of those basic mistakes with our exponents over here, great nights, where we say that it's 1 times 10, obviously we're going to get this wrong. But if we use our exponent knowledge correct, we know that 1 to the power of anything is still just 1. Even if you have 1 to the power of x, x represents a number, right? X represents 2 or 3 or a million or whatever. But it doesn't matter. 1 to the power of anything is just 1, because it will be 1 times 1 times 1 times 1 for however many times. Okay, so we simplified that one. 1 to the power of 200 is just 1, because it is 1 times itself 200 times. Now let's look at this one over here. Over here we've got a -1, which we need to just maybe look for a pattern there. Some of you maybe know this already. -1 to the power of 1 is just -1. -1 to the power of 2 is equal to -1 times -1, which will give us +1. -1 to the power of 3 is equal to -1 times itself 3 times, which will give us a -1. -1 to the power of 4 is equal to -1 times itself 4 times, which will give us a +1. Note what's happening over here. Right, nice. So if we have an even exponent, then we get a -1. Or if we have an uneven exponent, sorry, we get a -1. If we have an even exponent, 2, 4, we get a +1. So we can obviously carry on with this pattern. So if we have -1 to the power of 11, since that is an uneven exponent, we're going to get -1 as our answer. If we get -1 to the power of, say, 20, that is an even exponent, and then we are going to get a +1 as our answer. So looking at this, 101 is an uneven exponent. So we will be able to evaluate that as a -1. Part of our pattern, the uneven exponents will have a -1, and then we need to add them. And when we add them, -1 plus 1 is equal to 0. So x to the power of 101 plus y to the power of 200, considering that x is -1 and y is equal to 1, is just equal to 0. Let me know what you think about this question. Maybe you could have done it in 5 seconds, and that's perfectly fine. But remember, we're trying to develop a concept. We're trying to see the need for sometimes to go spot patterns. Okay, next up. For the next question, it says calculate the area of a rectangle. They give us that it's a rectangle, and they also happen to give us the formula to calculate an area. Length times breadth. In this case, we have our length. It seems that our length over here is given as 8 to the power of x, and our breadth is given as 2 to the power of 2x. So we won't be able to get the area as like a number, like as 10 or 20 or whatever. There will be an x in our answer, and that's okay. So let's have a look. So for our area, they give us that it will be our length times our breadth. Okay, but now let's go substitute what they gave us. They gave us that our length is 8 to the power of x, and they gave us that our breadth is 2 to the power of 2x, and these two things are being multiplied. That's part of our formula for a rectangle's area, right? Okay, but now we're like, okay, wait, what? Some of you might say, I think a common error would be that you would just say 8 times 2, maybe you would multiply the basis and then maybe add the exponents or something like that. It's definitely not that. We need to go back to our laws of exponents. So we also need to think about our laws of exponents, grade 9s, whenever exponents show up, not just in the step-by-step sums that we are used to. So how do we multiply when there are exponents involved? Doesn't the law say when our bases are the same and we're multiplying, we can add the exponents? The law definitely does say that. But in this case, our bases are not the same, and that is the problem. So that is where we need to kind of tweak and see what we can do about that. Isn't there potential to make our bases the same? Well, 2 is just a prime number, so that's going to stay what it is. But isn't there potential to write 8 as a base of 2? Can't we rewrite 8? We're not changing to the value of 8. We are just rewriting 8 as 2 to the power of 3. Because 2 to the power of 3 is equal to 8. We're not changing to the sum. So we are taking that 8, we are rewriting it as 2 to the power of 3, and we are just keeping the original exponent. So note what I'm doing. I am taking, here's my 8, I am rewriting my 8 as 2 to the power of 3, and we can't just throw away that exponent. There it is. And then we just multiply those two. Power raised to a power, right? So 2 to the power of 3x. Same thing. We're not changing to the sum. We rewrote 8 to the power of x as 2 to the power of 3x. Now, our bases are the same. When our bases are the same, and we are multiplying, we're going to add our exponent. So it will be 2 to the power of 3x plus 2x, which is equal to 5x. And that represents the area of this rectangle. So many ideas involved. Laws of exponents, prime bases, adding like terms, area of a rectangle. But I think this is a really nice challenge. Let me know what you thought of it. Now with the third one, a certain bacteria doubles. So if something doubles, we are timesing it by 2, hey, in size every hour. So in 1 hour, it will double. Then in the next hour, that value will double again. Okay, we need to visualize that idea. If the initial population, so in the beginning, at first, the population of this bacteria is 500. Okay, the number of bacteria after T hours. So that's just a variable representing, it can be 1 hour, 2 hours, 1.5 hours, is given by this formula. Okay, so let's make sense of this. So our P stands for our population of how many bacteria there are or is, whatever. That is the initial amount. So in the beginning, that's how much there was. Why is there a base of 2? Because we are doubling. We are doubling. And then our T exponent is 4 times. So if we substitute a 1 in there, it will be after 1 hour. If we substitute a 2 in there, it will be 2 hours. How much bacteria there will be. Okay. So thank goodness they gave us that. Now they're saying how many bacteria will there be after 6 hours? Now, if we were to work that out, we can do that without the formula, surely. And I'll show you what that would look like in a moment if that was maybe your instinct. But let's just plug it into that formula, that equation that we got to work with. We've got the population will be 500 times by 2 to the power of 6, because it is 6 hours. Let's work that out. Well, that will be 500 times what is 2 to the power of 6? Let me just reach for my calculator. I think it's 32. 64, I was wrong. 64. And if we then, how can we work that out fast? I mean, we can times it by 1,000 and then just divide it by 2 if we want to work it out like that. So that gives us 32,000. I hope you got the same. I hope that's correct. Let me double check. Yeah, I think that's fine. Okay, so that's how much bacteria there would be after 6 hours if it doubles every single hour. If we were to work this out without a formula, what would we have said? Well, I guess we'd have said after the first year, we doubled the 500 that was there originally or initially, and that would give us 1,000. Then for the second year, we would double that, which would give us 2,000. Then for the third year, we would double that, and we get 4,000. And then for the fourth year, we would have 8,000. For the fifth year, we would have 16,000. And then after the sixth year, we would have 32,000. So that formula is just built on this idea and that. Okay, let's see what is next. So for the second question, it says, express your answer in scientific notation. Okay, so now we need to represent the 32,000 as scientific notation. So let's quickly just remember how that works. We need the comma to be between the 3 and the 2, right? Let me just go write down that formula for our scientific notation again. So what does that look like? Scientific notation takes on this form. A times 10 to the power of p, where p is an integer. That's any negative or positive number. It just can't be 0. This must always be 10. And our a must be smaller than 10 and bigger or equal to 1. So it must be a number between 1 and 10. So it must be a number like, for example, 3,78, that where there's 1 digit in front or before the comma. So we want our comma. Let me just write that over. So for our 32,000, we want our comma to be there. Where is the comma at the moment? Well, at the moment, the comma is there, right? Because it's just 32,000. So we are going to move it 1, 2, 3, 4 to the left. So let's go write that as our scientific notation. So that would be 3, 2. There's our a times by our 10. Let's just talk about what our exponent is going to be. Well, we are making a big number, 32,000, a lot smaller. So it will be a positive exponent of how many times did we move the comma? 1, 2, 3, 4. 4. 10 to the power of 4. Let's see if that works. Let's just quickly do a double check. If I've got 3, 2, and I times that with the 4 zeros, 1, 2, 3, 4, then I will get, let me just make some space there. Then I will get 1, 2, 3, 4. Let me add those zeros, and that would be 32,000. Yes, so that works. And there we wrote it in scientific notation. Last question for this video. Let's read carefully. Often I find that students don't read and they don't get themselves into the context of the sum, where they see a problem that maybe they haven't seen before. Okay, a box. So we're dealing with the box. It has the following dimensions. So we've got a length, a breadth, and a height. So this should be a rectangular box that would look something like that, where we've got a length. Doesn't really matter where you put the dimensions and what you see as the length, because if we turn the box upside down, that will change. And the breadth is 4 to the power of x plus 1. And then the height is 2 to the power of 3x. Okay, great. So there we've got our dimensions for this box. Now you might be wondering, why on earth would they give it to us like that? Let's just forget about that for now. Okay, for the first one. Express the volume of the box as a power of 2. How do we get the volume of a rectangular prism, so of a box? The volume would be length times the breadth times the height. So let's go plug that in there. The volume for this box would be the length times the breadth times the height, 2 to the power of 3x. Now, I think it's a really nice hint that they gave us there that we need to give it as powers of 2. Because if you think about it, grade 9s, there isn't much that we can do when we're dealing with exponents when our bases are not the same. So they are encouraging us over there to make our bases the same. Well, if we look at the last one there, that is already a base of 2, so that's perfectly fine. Let's look at the potential for this one over here. How can we make the 4 a base of 2? I'm going to write it on the side over here. If I take 4, it's the same as writing it as 2 squared, right? So let's just consider the exponent. I am rewriting. So I am rewriting my 4x plus 1. I am taking the 4 and I'm writing that as a 2 squared. I'm not changing to the sum. It just looks different. And that would then give me 2 to the power of 2x plus 2 because I multiply the exponent on the outside by the exponent on the inside, right? So we're dealing with some distributive property there. So we can write that as 2 to the power of 2x plus 2. And then for this one over here, how can we write 8 with a base of 2? Well, if I take 8 to the power of x, I am taking the 8 and I am breaking that up as 2 to the power of 3. It's still 8. It's just written as 2 to the power of 3. And now we have to multiply those exponents, which is 2 to the power of 3x, just using our basic laws of exponent. Okay, great. So we've made all our bases 2. So now the law of exponent says when your bases are the same and we are multiplying, the base stays the same. And we add the exponent. So we're going to have 3x plus 3x is 6x plus 2 more x's is 8x and then plus 2. And then we did what they asked us. The volume can be represented as that. So let's see in the next question. Oh, yes, in the next question, they actually do give us a value for x. So now in the next question, they're saying, if x is 3 for this specific box, calculate the volume of the box. So let's take the volume of the box. We can just use this one because that is the formula for the volume of the box. Would we get the same answer if we use this one? And if we use that one, absolutely. Now let's go substitute. Into the place of x, we are going to substitute 3. And then plus 2. Now stay true to that operation over there. It's 8 times x, so it must be 8 times 3. What is 8 times 3? That must be 24 plus 2 is 26. So the volume for this must be 2 to the power of 26. I'm not going to do that without my calculator. And that gives us something like this. And then that would be units cubed. Whatever the units are. If it's centimeters, meters, I can't imagine that it will be meters because that is an enormous box. And that's it for our fun challenges.